Thank you. So, hello everyone. I'm Jonas Jarutis from a company called Vertical, and I will talk today about my experience in image deduplication trying to use embeddings. So, in this talk, we will check what kind of challenges we wanted to overcome. We will very briefly review a few vector databases. We will check what kind of methodologies we can use for image duplication, and we will benchmark them, and in the end there will be a summary. This won't be a very in-depth talk, but more on the overview of possible tools and options for this task. So what's an embedding? An embedding is, we call embedding a vector, which is calculated usually using some kind of model. It can be neural network model, it can be other models. And how the thing works, some data object, it can be text, can be sound, can be image or video, is fed into the model, and the model produces a vector, a list of floats. And the model's job in this case is to produce those embeddings in such a way that similar objects would be mapped to vectors which are also similar or close one to each other in some embedding space. So that's why they're called embeddings. So we had an idea to use embeddings to solve two somewhat opposite but also somewhat similar problems in our daily job. So one problem is sometimes we have a data set with a lot of images, and due to some restrictions on screen real estate, we want to select a few of those images, but those images should represent the full data set as best as we can. And the other problem is simply storage optimization. We acquire quite a lot of images from various sources, and we wanted to find out if we can find duplicates of those images and reduce storage requirements. So let's look at the first problem. So for example, we have a set of images, and we want to select, let's say, 5 images from this data set, and some of them are very similar. So we can safely discard probably a lot of images seen here. So how can we think about it? Let's do a little demo. So I've created a small app using Streamlit. I believe somebody already talked about this software, and yeah, it's really good. So what are we doing here? So we loaded data set, which the same data set that you saw before. It contains 23 images, and we calculated an embedding for each of those images using convolutional neural network. I'll go into the details on that a bit later. So if we select, for example, that we want two clusters we want to divide those images into two clusters that would be most distinct between each other, so we can create those clusters in a way that we would be as far away from each other as possible. In this representation we do not look very far away. We are mixed a little bit because the actual vectors are 512 numbers, and we are reduced to 2 dimensions, so we overlap in this representation. But if we look at the photos, it works quite well. If we increase, for example, cluster size into 5 as we wanted in our initial requirements, so we can see that one cluster is of inside of the car, the other one is of the front seats, the third one is wheel, and the doors, and the final clusters are the car from the front and from the sides, and the last one is the car from the back. So it works pretty well. We can select one image from each cluster, and we will have a pretty good representation of the full data set in just a few images. Yeah, you can select some other set of images, and it should work also. Yeah. Yeah, so we can see that, yeah, the first is exterior photos, the front seat, the back seat, front panel, and yeah, the doors for some reason. So in this method, we can't control fully what kind of those clusters are, but if we do not know in advance what specific parts of the data set we want to show, but we just want to reduce a large data set to a small one, it works pretty well. Yeah, so this we already implemented this feature, and for example, here is an example of images that yeah, the same method was applied, and I believe the top 5 images represent the full data set quite well. The other problem is a bit harder, so the rest of the talk will be mostly about that one. We have quite a lot of images, as I said, and what do we mean by duplicate images? So if we would mean that the image should be exactly same byte by byte, it would be an easy problem. We could calculate some exact hash like SHA or MD5 and compare those hashes between images, and the problem would be solved. But since we get images from different sources, we can be slightly modified in various ways. So they can be in different file formats. For example, in one case it might be JPEG, in another case it might be PNG images, and so on. They can have different quality settings. They can be cropped a bit. They can be in different sizes. And we will check what kind of methods that we can use to detect the duplicated images despite these modifications. In order to do that, we will need one tool. So we will check in our proof of concept, we'll check about 1.5 million images. In order to work with that efficiency, we need a vector database to put all those embeddings into. And there are quite a lot of databases to choose from. There are open source databases, there are commercial offerings. Also, at the moment, most of the regular databases also have some kind of extension or support vector functionality in themselves. So how to choose the right one? We selected 3 criteria. So we wanted to check the performance, we wanted the database to scale well, and we wanted it to be somewhat mature and have an active community so that we could find help on issues when we encounter them. This is still a proof of concept, so we selected 3 of open source available databases, and we did some small experiment on a local machine with default settings and default indexing methods. So take those results with a bit of grain of salt, because all those databases are pretty complicated, and there are a lot of knobs to tune to improve performance further. So if we look at those 3 databases, we see that ingestion time is similar in LansDB and VV8, but Quadrant was quite slower. On the other hand, Quadrant used the lowest amount of memory, so if that is an issue, it's a good choice. And the query times were the Quadrant was slowest in terms of query time, and VV8 performed best, and LansDB was close. So Also, LensDB, we selected LensDB because it performed well, and also it has very nice SDK for interactive use, for example, in notebooks. So it was a good fit for our use case. So let's look at what kind of techniques we can use to detect duplicated images. So as I mentioned, the simplest one would be to calculate exact file hash. It's extremely fast. However, it will not work if the file has any minor edits. So it will work only in cases where the files are exactly the same byte by byte. A little bit better and still pretty fast technique is called perceptual hash. So the idea of this technique is to compress images using various methods until you get a very small image. The exact size depends on the method of compression, and there are quite a few of them. But the very popular one, for example, leads to image of size of 8 by 8 pixels, and it can be converted to 8-bit hash, 8-byte hash. And it's really simply to use in Python also. There are quite a few libraries that support them. OpenCV also supports them, and it's just a few lines of code to implement this functionality. Another technique from classical computer vision is to use so-called feature-based matching techniques. So how we work, we detect key points in an image, and those key points stay the same despite various transformation of the image. So you can rotate the image, you can scale it, resize it, and it will still detect the same key points. So for duplicate image detection, you can, and it works in two stages. First, you detect the key points, and in the second stage, you match the key points between two images, which correspond to the same places of the image. And yeah, so for detection of duplicate images, you can calculate how much of those key points are matched between two images, how many matches are found. However, this method is very computationally expensive, and it also requires quite a lot of storage because there can be quite a lot of key points detected in a single image. And I wouldn't recommend it if you need robust matching between two images. I would recommend to look at neural network based methods. So if we want to use neural networks for calculating embeddings, we can use mostly probably any neural network designed for image classification. And how we work, in the last layers, we have the same embedding, and it corresponds to various features that was found in an image. So if the neural network was trained well, so those embeddings will be the same among similar images, and same images, it will be the same also, yeah. So the pros of this method is that it captures high-level semantics of the image, and you can train it to your specific data set. And there are lots of off-the-shelf models available, and it scales quite well with appropriate vector database, but it requires GPU for efficient calculation. And with large data sets, you will need to use approximate search, and there will be some misses. And the similar also technique is to use neural networks that produce multimodal embeddings. So the difference from the previous ones is that there are two different neural networks here. One is called text encoder, and the other one is called image encoder. And they are aligned so that text which has similar meaning produces the same vector as image which would be described by that text. So in some cases it's useful because you can use those for zero-shot search and image classification. You can say, for example, you can show an image and you can say, is this a photo of a cat, a photo of a dog, or something like that, and the one text that corresponds best to the image will have the highest similarity between embeddings produced. So let's check how good we work at detecting duplicates. So for this test, we indexed 1.5 million images, stored them in a LensDB vector database, and we selected a random sample of 1,000 images from those, and then distorted them in various ways. I'll show in the next slides how. And we checked what percentage of times querying using the distorted image produced the original image in the first result and among the top 5 positions. So yeah, all those mentioned embedding methods produces some kind of vector which was embedded into LensDB, and we selected the specific ones from those 3 categories for our test. Yeah, so one thing that we wanted to take account also is how expensive it's to calculate embedding. So with perceptual hash methods, it's much faster compared to neural networks based. But if we use GPU, neural networks also can be pretty fast. And also these times are if we want to calculate embedding for one image. In case of neural networks which work on GPU, we can speed up quite a lot by batching some amount of image into one set and calculating embeddings for all those images in one batch. So it would be probably ResNet would be close to block mean hash in such a setup. So what kind of image alteration did we did? So the first one thing is we tried different file formats. So images visually look the same, where bind content is simple is different. But all those methods should work fine in this case, and that's exactly what we see. We don't get 100% accuracy because there are actually some duplicated images in the data set, and the first one can be not the same name that we queried. So let's see if we resize the image, what will be the impact? So if the resolution is still quite large, but smaller than the original, the impact is also minimal. Only one method performed poorer. Not sure why. The convolutional network with large embedding size. But if we resize to a thumbnail-sized image, we get quite different results. So in this case, the simple perceptual hash methods still work well, because in their calculation, you have to resize image to just a few pixels, so it doesn't matter if it's a thumbnail size or original size. However, in a large data set, the embeddings already suffer quite a lot, and yeah, we get a lot of collisions. What if we change the quality of JPEG image? So again, if the quality is medium, all methods work fine. However, if we degrade it extremely, the neural network-based methods perform quite worse. What about cropped images? So in this case, the opposite is true, because for those hash methods, it's quite we need to see the whole image in order to calculate the hash. If we crop the sides, we get quite different hash. Those pixels are important for them, so we don't work in this case. But the neural network-based methods work pretty well. If we crop a lot, nothing works. Yeah, and what about some filters, for example, if we alter colors? So if we alter colors slightly, most of the models work well, but if we alter colors quite a lot, again, neural network-based methods suffer. So, summary. I was quite surprised, in fact, that I didn't expect such results. I thought that neural network-based methods will be much more robust to alterations than perceptual hash-based methods, but in turns out it's not like that. I believe that we could improve the results probably by a lot if you would have fine-tuned the neural network to our specific data set, and I haven't done that yet. Probably will do that in the future. So to summarize, if your goal is image duplication, the classical perceptual hashing methods still work pretty well. If you plan to use embeddings on large data set, you should probably consider fine-tuning your model on your data. On the other hand, neural network-based embeddings work great on small data sets. If you, for example, have a use case where you want to select different images to represent the full data set well, we work very well. And vector databases are very convenient to do such exercises. Thank you.
Now it's time for questions. Does anyone have any question? Anyone?
How much does the accuracy suffer if you do black and white? Haven't checked. Yeah, so it will not be any changes for perceptual hashes. I don't think that it will suffer a lot for embeddings as well, but not sure for neural network-based embeddings.
Is this integrated in the product car vertical?
So that part where we select a few images from the large data set will be integrated in the coming days, and we had a problem with our reports in PDF format. So in some cases we had a lot of images, and for one thing it's quite a lot just to scroll down through the full images in the PDF file, and sometimes it even broke the PDF file generation if there was like thousands of images. So we created this feature due to that, so it will be live soon. For the deduplication part, we are experimenting. If we need to check if it will produce enough benefits for us. Not sure yet at the moment. It's a work in progress.
Okay, thank you. I was working on a similar problem with just text embeddings, but lots of good ideas here. I just didn't connect what are you embedding exactly? The output of these neural networks or image bytes? Thank you.
So we need to calculate some kind of vector representation for the image. So in terms of perceptual hashes, we compress the image into a small amount of bytes, and I put that bit by bit representation into vector database. In terms of neural network-based methods, I take the output of last layers of neural network.
So in the first part where you showed that how to select 5 images or whatever, you used PCA, right? I think.
Yes, for that chart, but it's just for the representation of clusters in the graph. We don't use PCA in the image selection itself.
So you probably just use the vectors themselves, right?
Yes.
Yeah.
Yes.
Okay. Yeah.
The distance between cosine similarity between vectors.
Hi, Jonas. Thank you. How do you think you can make your solution more robust? For example, if you're not responsible to create a full data set yourself, if you have a bad quality of pictures.
So one thing that I would definitely try is to fine-tune the neural network model on your data set. So you probably you need to have some kind of metadata associated with the images. If you have some kind of metadata, like what is represented in the image, some labels or some textual description, you can use that to fine-tune the model. Yeah, I think it would work much better if it would be done. Yeah.
Okay, but what if we have like car under the rain or in the snow, for example, and we had to use such pictures?
Yeah,
just to fine-tune?
Yeah, fine-tuning would help a lot in this case, because if you would fine-tune, like for example on the car model, and you would have examples of those cars in different conditions, then the vectors would be much more robust to those differences in the background. It would focus only on the car itself, not the differences in the backgrounds.
Okay, thank you.
Thank you. Could you go over a bit more detail how you created your top 1 and top 5 accuracy retrieval task? So you took the images, you distorted them, and you checked to go back to your good one?
Yeah,
and,
so
and particularly for additional retrieval tasks, for example, for text or other sorts of embeddings, things, other ways you could do this augmentation to create the retrieval test.
Yeah, so I'm not sure about text, how it would depend on what do you mean by similar text, probably, and what kind of alterations do you expect. But in the image case, so what I did, I indexed the original images like they are in the databases. And I created, like, for example, changed the colors of the image. I created 1,000 of such images. I made with that altered images 1,000 queries to find the most similar vector, closest vector in the database to the one that was produced from the altered image. And if I checked if those the search results represent the original image in either the first position or within the top 5 positions. So I calculated new embedding for each of those altered images and did a vector search based on that new embedding. So with text, you probably could do something similar, just you need to decide what kind of alterations to the text you need. What kind of alterations you would like your system to be robust to.
Okay, that's the last question. Sorry. Oh, yes. Sorry.
In your platform, will you be always showing top 5 images, or the amount of top images will be dynamically adapted to each case?
It probably will not be dynamically different. We didn't want to do that, but the requirements might change, but it won't change automatically. So we will probably need to redo something manually if we want different images, but different set of images. Because in that solution that will be live in production, we also use some addition models also to select more specific images. For example, we do want to show always image with damaged car if it exists. So we use a second model for that. Also, we wanted to show a front panel always if it exists. So we also used a second model for that. So it's a combination of things. And we select some specific images if they exist, and what spaces are left, we fill based off this methodology.
Thank you so much, Jonas. Thank you,
Thank you.
everyone.